Any questions at all before we get started? Things are going all right? Yeah. All right, so last time we came up with several different properties for determinant. So I'm going to do a few more things with that, and then we'll talk about how we calculate the adjoint, which is what the video was about that I asked you to watch. How'd that go?
I watched it this morning during breakfast.
Oh, that's nice. To help your digestion? Yeah.
I think I'll understand it more once we do like this.
Sure.
So I guess the question I have, so you can use the adjoint to calculate the inverse?
Yep.
That seems a little bit more of a process than just...
It does. Correct. It is more of a process, yes. But you can do it, yes. Usually you would not do it. Yeah. But you can. So, all right. So last time we said that one of the properties that we had for determinants is that it breaks up over products. Is it true that determinants break up over sums? Is this a true statement? Well, let's think about a specific example. What would be the determinant of that matrix? It'd be 0, right? You could calculate it directly, just how we talked about the 2x2s, but what property of that particular matrix tells you that it definitely has a determinant of 0? Yeah, the column of zeros or the row of zeros, either or, right? Definitely tells you that the determinant would be 0. Or if I did this matrix, what would you get for its determinant? Also 0, right? But what matrix do you get if you add those two together? What is the matrix that you get? Yeah, which is what special matrix? It's the identity it's the 2x2 identity, right? And of course the determinant of the identity matrix is 1, right? So this is not true. Remember, we did have an additive property for determinants, but what had to be true about the rows? There was some sort of an additive property for determinant, but something had to be very, very specifically true about the rows. The two matrices had to be identical except for one row, and it was just the rows that got added together. Right? So there is an additive property, but it's an additive by individual row. Right? The other rows have to stay the same. So in general, it's not true that determinants break up over sums. But there are some other properties that are true. This one should be fairly straightforward. How do you think we could do the determinant of a transpose? How do you think it relates to the original one? If it were negative, we would have to be flipping rows, right? Swapping rows. What does a transpose do?
The columns on the rows.
Yeah, it makes it rows, columns, and columns, rows, right? Well, one of the ways that we can calculate determinants is expanding along any row we would like or any column we would like, right? So say I wanted to expand along row 2 for the transpose. What would that be the same as expanding along, essentially? The column 2 for the original, right? So does the determinant going to change at all? No. Okay, so this is actually the same as determinant of A. So the transpose doesn't do anything at all. What about if we had an n by n matrix and I asked you for the determinant of some constant times A? Do you think this is just C times the determinant of A? Again, think about how we started off our discussion with determinant.
No,
It wouldn't, because why?
because C times determinant A is when we just take the C times one row.
Good. Remember when we do the C times one row, that's when we multiply the determinant by that constant, right? How many rows have been multiplied by C in this case? All of them. So if A is an n by n matrix, how can I fix my equation to make it true?
C to the n.
C to the n. I would have to pull off a C for every single row, right? Right? Because this C gets multiplied by the first row, the second row, the third row, all the way down to the nth row. Every time you multiply a C by a row, it changes the determinant by a factor of C, and you do it n times. So that's where the C to the n is coming from. Does that make sense? Right. So let's say we do a specific example here. Let's say that A is a, let's say a 4 by 4 matrix. Such that, let's say the determinant of A is -5. Let's say I ask you, what's the determinant of A transpose? What would you tell me? Okay, -5. What if I asked you for the determinant of A inverse? Talked about this last time. Good. Yep. -1/5. Remember, the determinant of the inverse is 1 over the determinant of A. What if I asked for the determinant of A cubed? What kind of 125? I mean negative, right? Because I've got to cube that negative too. Yeah. So remember, determinants break up over products, so you can pull powers out as well, right? So the determinant of A cubed is the same thing as determinant of A quantity cubed. So you can just cube the -5. What about if I asked you for the determinant of, how about 3A? How are you coming up with 108?
3 to 4 power.
Okay, that's not 108.
-400.
Yeah, so we would do 3 to the 4th times determinant of A. That's the last property we talked about up here, right? This one up here. 3 to the 4th is the same thing as 9 squared, so that's 81, right? 81 times -5 gives us -405. I figured that's what you were doing, just miscalculated. It did have a 1 and an 8 in it, though. I mean, that part was good. All right, these ideas make sense? Yes. Because remember, this 3 gets multiplied by every single row of A, and A is a 4 by 4. So since 3 gets multiplied by 4 rows, I have to do 3 to the 4th for the determinant. Is this okay? You've got a problem like this in your homework. It's problem number 5 on page 110. Any questions about those properties at all that we talked about? Not too bad? All right. Pardon me. One of the other things that gets discussed in this particular section is an idea that I had put on your last test about solving a particular type of homogeneous system. So let's look at, this is problem number 14 on page 110. And in this problem, I just want to do part A. They give you a system of linear equations the first equation is x1 plus 2x2 equals lambda x1, and then 2x1 plus x2 is lambda x2. We're going to talk about this kind of idea a lot when we get to chapter 7 later in this semester. I'm going to introduce some of the words now, but this idea pops up later, and I want to talk a little bit about why we care. So let's rewrite this linear system in matrix form rather than in the equation form. So what would your coefficient matrix be for this particular system? What are the coefficients that we have?
1, 2.
Yeah, 1, 2, 2, 1. And then we would have the column matrix of x1, x2. And on the right-hand side, I could write that as lambda times x1, x2. All right. So we already know that it's not too hard to see that if you plug in 0 for x1 and 0 for x2, you get a solution, right? Because you'll get 0 on both sides. We refer to that again as the trivial solution when you have the 0 solution works. That's not a very interesting solution because no matter what multiplication I do, I get 0, right? However, if I can find non-trivial solutions, if I can find x1 and x2 that aren't both 0, look at what this equation implies. Notice on the left-hand side, we have matrix multiplication, right? But on the right-hand side, I have scalar multiplication. Which one's easier to do, multiplying by a whole matrix or multiplying by a single scalar? The scalar, right? Especially from a computational standpoint. Now, think about the computations that you might have to do if you were doing a matrix that had maybe was 50 by 50 or 500 by 500. That's a lot more computations if you're doing those matrix multiplication versus if I can replace it with a scalar multiplication. Significantly fewer multiplications that you would have to do, significantly fewer computations. So if you can find non-trivial solutions to this equation, then you can, in certain circumstances, you can do any matrix multiplication that you'd ever want and replace it by scalar multiplications instead. And this has applications to dynamical systems. We talked a little bit about Markov process earlier. We had something moving back and forth between two rooms. I think I talked about that earlier this semester. But if you want to analyze long-term behavior of something, a discrete system that requires doing matrix multiplication over and over and over and over again, that's hard. If you can replace that with scalar multiplication, you can actually analyze the scalar multiplication and do that much faster. Okay. So this has applications to anything that can be described as a process that's repeated multiplication with matrix multiplication. If you can replace the repeated matrix multiplication with repeated scalar multiplication, you can start doing calculus things like limits. See what happens as it goes off to infinity. Those are kinds of analysis that you could do. We're not going to do that right now. Okay? We're just going to talk about how we would find these non-trivial solutions for these smaller systems. We'll do more of that stuff later this semester when we have a little bit more machinery. Because this is only interesting if you can do it for any vector that you'd ever want to plug in, and we need to talk a little bit more about how we might that might come about later. So I know I'm being purposefully vague. Okay. All right. So anyway, let's talk about how we can solve this kind of thing. Well, the first thing we want to do is we want to make this into a homogeneous system. So let's move all of our variables to the right-hand side so we just have the zeros on the right-hand side. So if we do that, you'll get x1 times, you'll have 1 minus lambda, and then plus 2x2 is equal to 0. And then you'll have 2x1 plus another 1 minus lambda, x1 is equal to 0. Right? If I just move those over to the left-hand side, factor out the x1 in the first equation, the x2 in the second one.
Should the top right one be x2?
Yeah, it should be an x2. Thank you.
Otherwise, it'd be very easy to prove.
It would be very easy, yeah. It would be very easy, you're right. All right. So if we make this into a matrix equation again, we just would pull off the coefficients and make it a matrix. The only difference is now on the right-hand side, we would have the 0, 0 vector. All right. If we were able, well, let's think about it in terms of just equations that you would have back in Algebra 1 class. If this were number times x equals number, how would I solve for x? If we were to say 3x equals 9, what would I do to solve for x? Multiply by a third, right? Get rid of the 3. Okay? That would give me a trivial, that wouldn't be trivial in that case, it would give me x equals 3. If you were solving 3x equals 0, you would get the trivial solution in that case, right? Because you would just have x equals 0. Okay. The only way you could have something times x equals 0 not have trivial solutions is if you put 0 on the right, on the coefficient on the x, right? You have 0x equals 0, and then any x will solve it. Okay. All right, let's go back over here now to this particular equation. What's the matrix analog to dividing by 3? Multiply by matrix analog. I think about the matrix idea. Multiply by its. How do you do undo multiplication? Multiply by its inverse, right? So if I'm able to find an inverse for this matrix, what is the solution going to be every time? If I can multiply both sides by the inverse of this matrix, what answer am I going to get? 0, right? Because if I take the inverse times 0, 0, I'm going to get 0, 0, right? So if I can find an inverse to this particular equation, or excuse me, this particular matrix, I will get the trivial solution. That's the uninteresting case, right? I want non-trivial solutions. I want to be able to replace matrix multiplication with scalar multiplication in a meaningful way. If I already have 0, 0 as the only possibility, that's not meaningful. Right? I already know what multiplication by 0 is. Doesn't matter if it's matrix multiplication or scalar multiplication. Okay? I want to replace meaningful multiplications. I want non-trivial solutions. So if I'm going to get non-trivial solutions, what has to be true about this matrix? Okay, so we'll have to have infinitely many solutions to the system, so what has to be true about the matrix? Well, it doesn't necessarily have a row of zeros, but if I row reduce it, it does, right? So what does that say about the matrix? You told me that if it had an inverse, I would just multiply it over, we have trivial solution to this, right? Doesn't have an inverse, right? It's singular, right? Has no inverse, correct? So to get non-trivial solutions, the matrix 1 minus lambda 2, 2, 1 minus lambda must be singular. Singular again means not invertible. So to be able to get non-trivial solutions, I need to make sure that that matrix is singular. Now, also right at the end of class last time, we mentioned that we had a way to check whether or not a matrix was invertible using the determinant. right? What was that condition? Matrix is invertible if and only
Determinant is not.
if its determinant is not equal to 0. So if I want this matrix to be singular, what does its determinant need to be? 0, right? So we need the determinant of this matrix to be equal to 0. All right, we'll do this in just a second and solve it and go through. But notice what this matrix looks like. Notice it was the original matrix, except that I've subtracted lambda off the diagonal entry, right? Generally, this looks like the original matrix with lambda subtracted off the diagonal. So it looks like A minus lambda times I, right? It's your original matrix, and we're subtracting lambda down the diagonal. If I do lambda times I get lambda down the diagonal, right? This has a name. This is referred to as the characteristic equation of A. All right, so now we can just solve this. Well, this is an easy determinant to take, isn't it? For this particular example. Do 1 minus lambda squared minus 4. Right? Because it's 1 minus lambda times 1 minus lambda. And then subtract off the 2 times 2. So this is lambda squared minus 2 lambda minus 3. Is that factor? Okay. What does the factor as?
Lambda minus 3 and lambda plus 1.
Okay. So we get 3 and negative 1. These values that we have also have a name. These are referred to as the eigenvalues of the matrix. So the eigenvalues are solutions to the characteristic equation. We didn't do it with determinants on the exam, but you had something like this for the exam, right? I asked you for values that made a system have non-trivial solutions, where it was subtracted on the diagonal. Yeah, this is the same kind of idea. With determinants, a little bit easier to find it rather than go through the row reduction. You don't have to worry about dividing by variables and all those kinds of things. But these are your eigenvalues. All right, so once we have these eigenvalues, these are the values for which you do have non-trivial solutions, so we want to figure out what those non-trivial solutions are. So we go back to the original. If we put in lambda equals 3, our matrix becomes what? Negative 2, 2, 2, negative 2? Because you'll have 1 minus 3 and 2, and then 2 and 1 minus 3. And then remember on the right-hand side, we've got a 0, 0. That's our homogeneous system piece, right? This is now where we're at the point in the semester where I'm not going to expect you to do the row reductions by hand for these kinds of problems. I will ask you on the next test to do a determinant by row reduction, but that's the only thing where I'll actually expect you to do it by hand and show me the steps. At this point, we need to be able to use the calculator to do the row reduction so that we can interpret what's going on. Okay? And this is one of the things that we want to do. All right, so to have the matrix, I don't really even need the 0, 0 here if I remember that it's there. Right? Okay. So this has, we always should, when you do this, you should always get at least one row of zeros because we're finding values for lambda that give us non-trivial solutions. If you plug this in and get the identity matrix, you've solved the equation wrong. You should always get at least one row of zeros when you do this row reduction after plugging in one of the eigenvalues. Okay? So if you get the identity matrix and you do that, you've plugged in the wrong value. Okay? Something is wrong. Okay? All right. So this says that x2 can be anything, right? We got the pivotless column. So what does x1 be in that case? Also t. So if we write that in matrix form, oops. So we get t times 1, 1. All right. So before we do the other one, this also has a name, by the way. These are all the solutions here. These are the eigenvectors. Oops. I can spell vector, right? Associated with lambda equals 3. What this means is that if I look at the original equation, or the original matrix, and multiply it by 1, 1, I should get the same thing as 3 times 1, 1. Okay, so let's just look at that real quick. The original matrix was what? 1, 2, 2, 1? If I remember correctly. If I multiply that by 1, 1, what do we get? Well, 1 times 1 plus 2 times 1 gives me 3. And 2 times 1 plus 1 times 1 gives me 3. That really is 3 times 1, 1, right? So multiplication by this matrix by a vector in this form is the same thing as 3 times the vector in that form. We can do another one. It doesn't have to be 1, 1. It can be any scalar times 1, 1, right? So if I did 1, 2, 2, 1 times negative 7, negative 7, you would get negative 21, negative 21 when you do the multiplication, which is the same thing as 3 times negative 7 and negative 7. That's the idea behind this. The matrix multiplication is the same as the scalar multiplication for vectors of that form. Doesn't work for all vectors, it's for vectors of that form, right? The trick is, with these, later on the semester again, the trick is if I have some arbitrary vector, can I rewrite it in terms of eigenvectors to be able to do this for any vector? The answer is sometimes. Depends on the matrix, okay? So, literally, the answer is sometimes. Like, you can't do it all the time. There's cases when you can't do it. But if you can do it, then you can do this type of analysis that I was mentioning of what happens, long-term behavior of things, for example. All right, let's find the eigenvectors associated with negative 1. If we put in negative 1, the matrix becomes 2, 2, 2, 2, doesn't it? If you row reduce that, you get that matrix. So what do your solutions look like in this case?
X2, T.
Okay. Good. So I can write that as t times negative 1, 1.
You get the negative from the like positive negative thing, or how do you get x2?
So remember, the x2 is t just because that's the free variable. The negative comes in from this equation as x1 plus x2 equals 0, and I have to move it to the other side. So that's where the negative's coming in. So just rewriting it back as an equation and solving. So let's do this one again. If I take 1, 2, 2, 1 times negative 1, 1, what answer do I get? One negative 1. Does that make sense to what I should have got? Because what should it be? If this is an eigenvalue and eigenvector situation, what answer should I have gotten? In negative 1 times the vector we plugged in, right? Are those the same thing? Yeah. Okay. So that really, and again, any constant multiple of this vector will have the same result happen. So again, I can replace matrix multiplication with that scalar multiplication with that one's really easy because I just have to flip all the signs. Right? So right away, without even doing any work or any thought, I would know that 1, 2, 2, 1 times negative 75, 75 is 75, negative 75. I know all it does is flip the sign. I don't have to actually do the computations. Now again, you're probably thinking for 2 by 2 matrix, it just doesn't take that long to do the computation. However, if I had a 50 by 50, it would take a long time. And by the way, in terms of actually solving systems of equations, 50 by 50 is really, really small from industry standards. There are certain things that you have to do with, linear optimization, for example, that require several hundred variables that have to be thought about and analyzed and those kinds of things. So, yeah, this seems silly from a 2 by 2 standpoint. But if you're imagining trying to do this, say, a 300 by 300 system, that's a lot more computations you have to do, right? And honestly, a lot of these things that pop up have lots of variables that turn out to be 0 at any given time. So you have what are referred to as sparse matrices. Sparse matrices mean there's relatively few non-zero entries in them. And then you can take advantage of those situations too to be able to cut down on the number of computations. And again, if you're solving large-scale systems from a programming standpoint, saving time is a big deal. So, all right, anyway. Besides all of that, any questions on the actual process for being able to do this? The process is fairly straightforward, right? Subtract lambda off the diagonal, take the determinant, figure out the solutions. That gives you the eigenvalues. Plug them back in to figure out your solutions. It's not anything different that we've done earlier this semester for solving equations.
So it's kind of like finding a closed form for a recursive sequence.
Yeah, yeah, it is. It's because you can think of it as if you've got some sort of a recurring relation, then you can figure out the pieces that do it. So it's similar to that because the next step in the sequence, it depends on previous steps. Yeah, it could be thought of as a recurrence relation as well. All right, so let's talk a little bit about the adjoint, which was in the video. So again, the big things about the adjoint are how to get it. So let's just say as an example here, By the way, I'll never make you do anything bigger than a 3 by 3 because there's a lot of computations. Okay, so let's say A is 1, -2, 1, 0, 5, 2, 3, -1, -3. Doesn't matter. And we're going to create a new matrix out of this one that we refer to as the adjoint. So to get to that new matrix, we have to get what are referred to as the cofactors.
Is that a -3 and what?
Yeah, it's a -3. And the cofactors are exactly the same as they were when we did the expansion by minors, expansion by, I do a cofactor expansion for a matrix. So when we do the cofactors, there's going to be 9 of them. So we use the C with our subscripts here. So this just means the cofactor associated with row 1 and column 1. How we get that cofactor is, okay, we take row 1, column 1, and get rid of it. So I eliminate this row in that column. And I write down the matrix that's left. And I'm going to take the determinant of it. So this, without the determinant bar, but this actual matrix here, this is referred to as a minor. And in particular, this would be the 1, 1 minor. We've already done this, right? When we did expansion by minors, expansion by cofactor, the cofactor expansion determinant pieces, right? The only thing that we did a little bit different, well, not even different, we just multiplied by the coefficient that was out in front, right? All this does is, when you're doing the cofactor, you ignore the coefficient, but you do still keep track of the sign, which you can use your sign board to do, but if you like the formula piece, you can get the formula by doing -1 to the sum of the subscripts. So -1 to the 1 plus 1. All this is good. This just keeps track of your sign board. Just algebraically keeps track of it.
That has nothing to do with, like, it's not an exponent, it's just.
Oh, it is an exponent. It's just it flips the sign according to what the sign board does. Because notice if you do the 1 plus 1, you get 2, so that makes it a positive 1. That will be up in your upper left-hand corner. As I go across the row, it'll alternate because this number will go up by 1 each time. Or if I go down the column, it'll alternate because that number goes up by 1. And then if I go to the diagonal again, if I do a 2, 2, it'll be a plus in the diagonal, and you can keep going that way.
And that's just for the outside, right? That doesn't.
It's just for the outside, right? It's just going to be yeah. It's just going to whatever the determinant you're going to multiply by plus or minus 1. Okay. So this gives us what? Positive 17 when we simplify it. 15 minus a minus 2. Oh, I missed the negative. Sorry. Is that better? Negative 13. Forgot my negative, sorry. All right. So when you do this for adjoint, you need to do it for every single possible entry. So there's 9 cofactors here, right? Okay. So I need to do the 1, 2 cofactor, the 1, 3 cofactor, and so on down the line. Now in the video, I had them going straight across, right? Yeah. Doesn't really matter how I write them. I just need to make sure I put them in the adjoint in the correct order. Okay. So for your C12, I would have -1 to the 1 plus 2. I eliminate row 1 and column 2. So 0, 2, 3, -3 gives me a positive 6 in this case. If I actually wrote it down right this time. I eliminate row 1. I eliminate row 1 and column 2. We do 0, 2, 3, negative 3. And then I'll have a negative 6 when I do the determinant, but there's a negative out in front. So I get positive 6.
Is it the 0 times 3 minus 3 times 2?
Yep. By the way, if you want to keep track of these signs here with your sign board, that's fine. You just write plus and minus how you want to write them. You don't have to write in the exponent every time. Okay. Eliminate row 1, column 3. We get 0, 5, 3, negative 1. So that's negative 15 when we do the determinant, and it's positive out in front. So it stays negative 15. Are there any questions on where I'm getting these numbers? These numbers okay? Okay. All right, so if we do C21, I'm just going to write down the numbers just to save a little bit of time. We eliminate row 2, column 1. We'll get 6 minus a minus 1 gives me 7, and it'll be negative. So I get negative 7. Row 2, column 2 goes away. 1, 1, 3, negative 3. So I get negative 3 minus 3 gives me negative 6, and it'll be a positive negative 6, right? C23. I get 1 times negative 1, so I get negative 1 minus a minus 6. So I get positive 5, but it'll be negative because of the 2, 3 entry. I'm doing this more for time because I got about 7 minutes and I want to make sure I get this problem done and not have to hurry through the rest of it. And you told me you were okay with getting the cofactors. If that was a lie, then sorry about you, because I'm going to skip it now. Okay? 3, 1. Eliminate row 3, column 1. Negative 2 times 2 is negative 4. Minus 5 gives me negative 9. And it stays negative 9 because it'll be a positive entry. Row 3, column 2 goes away. 2 minus 0 is 2, but it'll be negative. Row 3, column 3. 5 minus 0 is 5, and it stays positive. So those are the 9 cofactors. Lots of computations to do the adjoint. So like Alex mentioned at the beginning of class, doing things with the adjoint is computationally expensive. Okay? But we can get to the inverse by doing the adjoint. All right. So in the video I went across when I did the cofactors, but usually when I'm writing them by hand, I do them down. And the reason for that is when you do your cofactors, the cofactors from the rows become the columns for the adjoint. It gets transposed around. The reason for that is, remember that when you do your determinant by cofactors, you want to multiply each of the cofactors by the coefficients in the matrix, right? Right? When we did expansion by cofactors, or expansion by minors, right? We did the coefficient times the cofactor, which is going to give us the determinant. If I think about setting this up with matrix multiplication, then I need to take the row of A and match it with the column. So that's why the adjoint becomes this transpose idea. So that when we do the multiplication, it matches up. Okay? So for your adjoint then, I'm doing it side by side up here. For the adjoint of A then, these were the cofactors for the row. First row, they become the first column of the adjoint. The second one here, these were the cofactors for the row 2. They become column 2 for the adjoint. These were your cofactors for row 3. They become column 3 for the adjoint. All right, so then something really, really cool happens when you multiply these two matrices together. At least I think it's really, really cool. All right, so let's do that. I'm going to pull these down so I have to rewrite them. All right, so there was A. Then here's an adjoint of A. All right, so what happens when we multiply these two things together? Oops, I'm not backing on. I'm not back on writing. That's why it's not writing. All right, so first row, first column gives me negative 13 minus 12. So negative 25, and then minus 15 gives me negative 40, if I did the math right. Okay. Before I do the other ones, I want to do the other two diagonal entries. Because if I've done this right, something cool should happen. If not, then I need to go back and fix my error. Row 2, column 2. 0 times negative 7 gives me 0. 5 times negative 6 is negative 30. 2 times negative 5 is negative 10. So I get negative 40 again. So far, so good. Let's do row 3, column 3. Negative 3 times negative 9 is negative 27. Negative 1 times negative 2 is positive 2. Negative 3 times 5 is negative 15. So minus 27 plus 2 minus 15 gives me negative 40. I get the same value down the diagonal, and that value has to be the determinant, the way we set it up, right? Because if we expanded along row 1, we would match it up with the cofactors that are in column 1 here. If we expanded along row 2, we would match it with the cofactors in column 2 here. If we expanded along row 3, same idea. We would match it up with the cofactors in column 3. So we have to get the determinant down the diagonal. And that happens every time. The other cool thing is what happens with all the rest of the entries. They're all going to be 0, yeah, because let's just check a couple. 1 times negative 7. Negative 7 plus 12 is 5, minus 5 is 0. Right? Negative 9 plus 4 is negative 5, plus 5 is 0. You can go through all of the rest of them, and they all are 0. So in general, if you take A times the adjoint of A, you get determinant of A times the identity. It's a really, really cool property of being able to do it this way. The determinant down the diagonal is not a huge surprise if you think about how we get the determinant by doing cofactor expansion, right? It's the zeros everywhere else that's the cool thing. But now, if A is invertible, then I can find a formula for the inverse by dividing by the determinant and multiplying it by the adjoint. So from what we just computed then, I know the determinant is negative 40. So the inverse is negative 1/40 times the adjoint that we just computed. The adjoint is computationally interesting. It's algebraically interesting. It's application very uninteresting because it requires way too many computations. Okay? Computationally, the adjoint is fairly useless. Okay? Algebraically, theoretically, it's an important thing. Actual practical purposes, no. You're not going to do it from a practical standpoint. It's just way too computational. You're never ever going to use it to compute an inverse. It's way too computationally expensive. It requires way too many computations to get to the final answer.
So it could be very easy to like miss a negative sign.
Oh, absolutely. Yes, there's all sorts of things you could do to mess it up. Yeah. All right. Cool. So that's pretty much everything with determinants. Have a good weekend.
Got any exciting plans?
Not right now, I don't. Grade some
I was
tests.
just gonna say grading our tests.
And we've got some statistics tests to grade later on.
That's good.
Yes.
Yeah, that's very exciting.
It's amazing news.
1 o'clock. Yeah, right after Athens.
See ya.
Yeah, I know. I figured I'd pick up on
So you'll be back in your office at 11, right?
Yep. I'll be back in the office at 11. Yep.
Great. I will be ready with questions.
Okay.
I'm so